In a given computer system, we have a number, it could be dozens or hundreds or more, of processes running. Some of these are system processes and some are user processes. The user processes may belong to many different users. The system resources and the many processes running, system and user, must all be protected from corruption by processes belonging to other users. Whether accidental or intentional harm might potentially occur. We need to make sure that only processes that have authorization gain access to memory contents, files, and other system resources. So, protection mechanisms are the things we use to control access to the system resources. In general, a protection scheme involves both policy, what restrictions we wish to be able to place on access to resources, and mechanism, the means we use to enforce these restrictions. We can think of policies as being like the law and mechanisms as being like the police. Without laws, the police wouldn't know what rules to enforce. Without police, you could have great laws, but there would be no way to make people obey the laws. They could go around the laws and get away with it. We like to keep policies and mechanisms modular. We want to be able to change policies without breaking the underlying mechanism, or alternatively, install an improved mechanism without having to change policy. This slide summarizes what we were trying to do with protection. The fundamental principle underlying almost all protection schemes is the principle of least privilege. The idea is that we should only give each user, program, or system just enough permission or capability to do what it needs to do its job, but no more. The idea is that if that user or program should turn out to be malicious or incompetent, we want to limit how much damage they can do. For example, as a professor, I need access to certain rooms, offices, labs, and so on to do my job. But the university doesn't give me keys to every building on campus. They don't even give me keys to all the rooms in the building I work in. I only have keys to my department's main office, my office, and the specific labs where our classes are scheduled. That way, if I were to decide to steal equipment, or if I simply lost my keys and some unscrupulous person found them, the amount of damage they could do would be limited. So in designing an operating system, we need to build in mechanisms to identify and authenticate users. For example, a login and password unique to each user, and then use that information to determine which users are allowed to do what. In other words, access controls. And of course, we need to debug the access control mechanism itself as thoroughly as possible so users can't get around it. This is easier said than done, as proven in real operating systems. A system is a collection of processes and objects, both hardware and software objects. Every object has certain operations that can be performed on it. For example, a file can be created, deleted, read, written, executed, and so on. With respect to a given object, a process can have certain access rights which define, out of the set of all possible operations on an object, which ones this process is allowed to do. A protection domain includes the set of objects a process can access and the access rights it has to each. A system can have, and usually does have, multiple protection domains. They may be custom defined for each individual process, or several processes may exist within the same protection domain. The domains themselves may be distinct or overlap. Unix defines two general domains, user and supervisor. Within the user domain can be any number of distinct users, each identified by their own user ID. One user can be allowed to execute or use a file belonging to another user by setting its domain bit, or set UID bit. This allows the user ID of the process to be temporarily changed to the owner of the file and then changed back when the file is closed. We have to be careful about this scheme because if a file belongs to a high privilege user, for example root, which is the most powerful user, and that file's set UID bit is set, it can be used to gain access as root and do anything to the system. Multics is an older operating system that has multiple levels of protection domains in a hierarchical structure. The innermost ring, or ring 0, has the most privileges. The outermost ring, 7 in this case, has the fewest privileges. Every executing process has a current ring number counter to identify its current privilege level. It can access resources at that level or a higher numbered level. A process is given an access bracket within the range of which it can call procedures. Going outside this bracketed range causes a trap to the operating system which can allow access to lower or higher rings, but only under very specific controls. This is a very flexible system, but not particularly efficient due to the overhead involved. One very general model of protection is called an access matrix. This defines a set of domains, one per row, and objects, one per column, such that each entry at a given row and column contains a set of access rights. In other words, access I sub j defines which operations a process running in domain I can perform on object j. The access matrix provides us a means of expressing the policies that a given system has in place regarding who can access what and for what purposes. What we would still need, of course, is an actual mechanism that uses the information stored in the access matrix to actually enforce policy. Here is a simple access matrix with only 4 domains, D1 through D4, and 4 objects, 3 files, F1, F2, F3, and 1 printer. D1 has read-only access to F1 and F3. D4 has a superset of this. It can also access F1 and F3, but for writing as well as reading. D3 cannot access F1 at all, but can read F2 and execute F3. And notice that domain D2 is the only one that can print, at least for now. If access rights are assigned statically, then the contents of the table would never change. But if we have a dynamic protection scheme, this means entries in the access matrix can be added or deleted over time, or changed, allowing or disallowing certain actions. If users can create objects, for example files, then they need to be able to specify who has what rights with respect to the newly created object. The system then has to add a column to the access matrix representing that object. If the user can later change the access rights to the object, for example using the Linux chmod command, then the system would need to update that entry in the access matrix. When a process is run, the operating system normally determines which protection domain it runs in. This, in turn, determines which objects it can access and how. Our protection mechanism must protect the access matrix itself. It is an object just like all the other objects in the system. Actually, since every entry in the access matrix can be modified individually, each one is an object that needs to have access to it regulated by the system. There have to be defined operations on access matrix entries, and processes must only be able to access the matrix via those defined operations. We said before that the operating system generally assigns each process to a domain when it is run. It is usually desirable for a process to be able to switch to a different domain while running. We can add this capability to the access matrix by adding a column for each domain as well as a row. If access I sub j has the attribute switch, then a process currently running in domain I can switch to domain j. In this case, a process running in domain D2 is allowed to switch to domains D3 or D4. A process in domain D4 can switch to domain D1 if it needs to. And a process running in domain D1 may switch to D2. Notice that a process running in domain D3 cannot switch to any other domain. Now, what if we want to allow, in a controlled fashion, changes to be made to the access matrix by processes running in the various protection domains? We can do this by implementing 3 additional operations: copy, owner, and control. Copy rights in the context of an access matrix means the ability of a process executing in a given domain to give the same rights it already has with respect to a given object to other domains. Here, the copy rights are indicated in the table with an asterisk. In a hardware implementation, there would have to be a bit that could be set to indicate that a domain has copyrights to an object. So here we can see that domain D2 has read copyrights to file F2. Because of this, it can give read access to any other domain, which, as we see, it does to D3, modifying the first table into the second. By default, copyrights would be transferable, which would mean that a process in D3 could now grant read access to yet another domain. So the new entry should be read asterisk. What the table actually shows is a limited copy, which gives the new domain the new access right, but not the ability to copy it again. A third possibility is a transfer of rights, where the original domain gives up its access rights. The owner access right controls the ability to add new rights to an object or remove existing rights. So in this access matrix, any entry in which we see owner means that a process executing in that domain can change other entries in the same column. So here, domain D1 is the owner of F1, and you can see that it takes away execute rights on F1 from D3. Likewise, D2 is the owner of F3 and gives write access to domain D3. Copy and owner rights allow a process to change the entries within a given column corresponding to one particular object, such as a file. We would also need a mechanism to change entries in a row. In other words, change what a domain can do relative to all the objects. For this to work, once again, the domains themselves must be listed in the table as objects, as they were 3 slides back. This is that same matrix with control added as an access right. So in this case, domain D2 has been given control over D4, such that a process executing in D2 can add or subtract access rights from the D4 row. In this case, it removes read access by D4 to objects F1 and F3. We already know that real operating systems, such as Linux, implement access controls on files and directories. You've already practiced using the chmod program to add and remove access rights to your own files that you created as the owner. You could change your own permissions, the permissions for your group. Of course, in the lab, we didn't actually establish a user group, and for the universe of all users of the system. Each of these 3 domains could be given read, write, and/or execute access to a given file. Our book points out that you could apply the same sort of protection scheme to things that are not files. Our textbook points out Solaris 10 as an example of an operating system that does this. It applies the principle of least privilege in its RBAC, role-based access control scheme. Specific access rights related to certain system calls are referred to as privileges, and these can be assigned to processes or to roles. Users can be assigned a default role, and there is also the capability to take on a different role based on having its password. The idea is that a user should always take on a role that has just enough privileges to do what needs to be done, and no more. In a system where users, or roles, or domains can be given access rights to certain objects, we may likewise at some point need to take those rights away at a later time. This brings up issues including the ones we see here: immediate versus delayed revocation, selective versus general, partial versus total, and temporary versus permanent. If protection is implemented via an access list, it is fairly straightforward to implement immediate revocation of access rights, and it can be done generally or selectively, totally or partially, and permanently or temporarily, just based on when and how our code, in other words the operating system's code that manages the access matrix, does the modifications to the matrix. It is easy, relatively speaking, to do revocation however we wish to do it. If the access matrix is implemented via capability lists for each domain, then revoking access rights is somewhat more complex. Capability lists are associated with domains, whereas access lists are associated with objects. So when we want to remove access rights from an object, we have to find all the domains that might have access to that object. They're not all in the same data structure as they would be in an access list. Our textbook discusses several approaches that could be used to revoke capabilities from domains that have access rights to an object. All of these approaches have significant overhead associated with their implementation, whether it's reacquisition, backpointers, indirection, or keys. Our textbook goes on to describe a couple of systems that have capability-based protection schemes. These are Hydra and the Cambridge CAP system. Hydra has a fixed set of system predefined access rights such as read, write, and execute. It allows a user to define other types of rights. These are interpreted by the user code as it wishes, but the system provides the protection capability associated with those rights. Procedures that operate on objects must be accessed indirectly by capabilities. To perform an operation on an object, the capability must contain the name of the operation being invoked on the object as what the system refers to as auxiliary rights. Cambridge CAP is simpler than Hydra. It has two kinds of capabilities. Data capability is the normal kind. What is unusual is that in this machine, they built the support into the hardware, microcode in the CAP machine CPU. The second kind of capability is software capability, which is supported by the microcode but actually interpreted by privileged procedures in application code. It allows programmers to define their own protection schemes for objects they own while maintaining overall system protection even if application programmers make errors in their code. Protection in computer systems is normally achieved by the operating system kernel with some underlying hardware support. However, in some cases, protection features are built into high-level language compilers such that application programmers can more easily incorporate protection mechanisms into their code. This may come in the form of specific data types that declare protection attributes along with content. In any case, the compiler must rely on the capabilities of the underlying operating system and/or the hardware to actually implement the protection. The Java Virtual Machine has a number of built-in protection features. As you know, everything that is defined in Java is part of a class, and every class is assigned to a protection domain when it is loaded. The protection domain a class is assigned to determines the permissions it is given. Which domain is assigned can depend on the source of the class. Was it downloaded from a trusted site? Does it have a verified digital signature? We'll talk about what that is in Chapter 15. Of course, there is the issue that methods within one class can call other methods, or library functions that may have come from a different source and may be assigned to a different protection domain that is more or less trusted. So the Java Virtual Machine has to have some mechanism for determining whether a given access is to be allowed or not, given its origin. The way it implements this is called stack inspection. Every thread running in the Java Virtual Machine has a stack of currently invoked methods. When code attempts to access a protected resource, the check permissions method is invoked, which does a stack inspection to look backwards through the stack of methods, starting with the one accessing the resource and going back to the one that called it, the one that called that one, and so on. If check permissions first finds a stack frame that has been given the doPrivileged annotation, then the access is allowed. If instead a stack frame is found for which this method doesn't have access privileges based on the protection domain it is in, then the access is not allowed and an exception is thrown. If the entire stack is inspected and neither of the above is found, then it is uncertain whether the access should be allowed, and what happens is implementation dependent. In other words, some Java virtual machines may allow it while others may not. In the example here, the call to the get method will succeed because the class it is in belongs to the URL loader domain, and it called open from within a doPrivileged block, which had permission to open that URL. But the direct call to open from the untrusted applet will fail because there is no doPrivileged annotation in the stack frame of the GUI method. This concludes our discussion of topics from Chapter 14.